So it gives me great pleasure to welcome today's speaker, Professor Peter Budd from the University of Manchester, where he is Professor of Polymer Chemistry. He did his degrees, his undergraduate and his PhD in chemistry in Manchester, and then worked for a few years as a research chemist at BP Research before returning to Manchester as a lecturer in 1989, I think. And his research seeks to understand the interactions between polymers and small molecules, and you can see from the displays at the front here where I think we're going to learn a little bit more about that this afternoon. He works on something called PIMS, which isn't what you think it is. I'm told it stands for Polymers of Intrinsic Microporosity, and we might learn a little bit more about that this afternoon. He's also a member of his local church in Manchester, and he is a lay reader in the Church of England. So it's a pleasure to welcome you this afternoon. You're going to talk to us on materials, membranes, and motivations for research.
Okay, thank you very much. And, it's an enormous pleasure to be here. And well, you've heard a little bit about me, so I'll just say a tiny bit more, because my parents actually worked for a missionary organization, which means I was born in Africa. I was born in Asmara in Eritrea and moved around a little bit. Ages 2 to 4, I was in Aden, in what is now Yemen. And then ages 10 to 14, I was back in what was then part of Ethiopia. So I've moved around a fair bit. My first school was a Church of England school in London, and then I had 4 years at a tiny little mission school in Asmara, and my final 3 years were at a boarding school in Ramsgate, St. Lawrence College, and we have another old Laurentian here, which is great. I have to say, when I first came back to England, a boarding school is a very, very strange experience when you've been at a very small school in Africa before that. But we survived. We survived. But that does mean that a lot of the people who taught me science and inspired me to do science had a very profound belief in God. Particularly had a superb teacher in Asmara, who was actually a graduate from in natural sciences from Cambridge. And she really inspired me and helped me to get interested in science. And later she worked in the most remote place on the planet, Tristan da Cunha, and then for many years in Nepal, and she got an OBE for her work in education in Nepal. But because I was actually taught about science to a large extent by people who had a deep faith in God, I often find it really weird when people seem to think there's some sort of conflict between science and faith. It kind of doesn't make sense to me. And maybe we'll say a little bit more about that later. But that's a bit about my background. So I traveled around for school. I went to Manchester for university. I got my PhD in 81 and went to work for BP in the 1980s, at a time when they were actually worried that the oil would run out by the end of the century. The order of the day was diversification, all sorts of interesting things going on at Sunbury-on-Thames. And what's been really good today is meeting up with Mary Vickers, who was at BP when I was there and has been working here in Cambridge for quite a while since then. And then in 89, I went back to Manchester as a young lecturer, and I haven't escaped since. But there is another side to my life, because I'm also licensed as a lay reader in my local church, which means I get to preach and lead services and things like that. So I have my foot in two camps. On the one hand, I'm a scientist doing scientific research. On the other hand, I also interact in church and in trying to help people develop their faith. So I'm someone who I don't study the interaction between science and faith, but I work at that interface, I guess. And so I'm going to tell you a little bit about the science that I do, and also a little bit about why I do the science that I do. And so the first word on the title is materials, and materials, that's really all of the stuff around us that we can make use of. And I'm a professor of polymer chemistry, so the materials I'm particularly interested in, those that are made up of really, really big molecules. I like big molecules. And in particular, we're interested in how they interact with little molecules, and we'll see a little bit about how we can use that. And being at Manchester, there's something I haven't been able to escape, which from my perspective is just a very specialized polymer. and that's graphene, and I'll say a little bit about that as well. It's only a short afternoon, I can't talk about everything, but we'll see a little bit about where we can combine two materials to get better performance than you would get from each alone. I've also, and I'm not going to talk anything about this today, I've also been involved in some work in the sort of bio materials area, looking at things which are good for getting bone cells to grow for tissue engineering and such like. And something that I've been interested in from time to time is how we can get new and useful materials out of natural products. Not often much money in that, so it's something which comes and goes. But those are the broad areas I've been working in over the years. And in terms of the particular focus of a lot of our research, well, a lot of it is summed up actually in a comment that David Scholl and Ryan Lively at Georgia Tech wrote in the journal Science a little while ago. And they pointed out that a chemist like me, in industry, an awful lot of time and energy goes into separating mixtures. And as they say, most industrial chemists spend their days separating the components of large quantities of chemical mixtures into pure or purer forms. And the sorts of processes that are used, which is often distillation, for those of you who know about that sort of thing, they're energy hungry. And in fact, estimates of 10 to 15% of the world's energy goes into separations of one kind or another. So there is, here have, if you like, one of the motivations for research, which is trying to do things much, much more efficiently. And one way of doing that is through membrane processes, and that's something I'm going to say a little bit about. Now, when I say the word membrane, those of you who have a background in the life sciences probably think phospholipid bilayers and biological membranes, and I'm talking about something completely different, which is any thin film of something that's useful as a selective barrier. And so in the simplest case, it's just a thin film of polymer, something like a plastic, although in reality it's much more complex than that. But the idea is that we have a barrier that we can use on an industrial scale that will let some things through relatively readily and not others. And so we might be wanting to separate gas mixtures, and one example that we're interested in is how you can pull carbon dioxide out of flue gases. It might be from power stations, but also from things like cement works, which are actually large producers of carbon dioxide. And how you can do that energy efficiently, because the current technology could, if you wanted to put it on a power station, it could use a quarter or more of the energy of that power station just for the process of removing the carbon dioxide from the flue gases. So if we can do that much more energy efficiently, that creates real opportunities and on scale. And then we might want to separate liquid mixtures, so we have polymers, as we'll see later, that will pull an alcohol out of water. It's easy to mix them, much more difficult to separate them. And of course, an area which is very, very important, large numbers of people have difficulties in accessing pure water supplies, and purifying water for one reason or another is a big area of activity and something that also interests us. So I'm just going to touch on a few of these things in this talk. Haven't got time to talk about everything. But it gives you an idea of the sort of thing that interests me. And one reason for that is that that we actually want to make the world a better place. And you may be familiar with the the global goals for sustainable development that were agreed in 2015. 17 goals with lots of targets under each goal. But the idea is that if we can achieve these things, we can make the world a much more sustainable place. And of course, a lot of the issues here are political and social issues. They have to be addressed through politics, through societal change. But there are also areas in which we as scientists or engineers can contribute to finding solutions to some of the problems that exist. And so I'm going to, it's a little bit faint on this screen, but I'm going to first focus on three areas of interest, three of those global goals. One is about, you may be able to read it, just about clean water and sanitation. One is about affordable and clean energy. One is about climate action. And in particular, all of these things have issues which involve separations. And so there are technical challenges to be addressed in terms of performing those separations much more efficiently, whether it's desalinating or otherwise treating water, whether it's new forms of energy, and biofuels is one option that I will just mention on the way through, whether it's how we deal with the carbon dioxide emissions that most people accept contributing to climate change. So I'm going to touch on a little bit of those things, not in great detail, as we go through the talk. So materials, membranes, and why we do what we do. And let's begin with some materials. And you may be aware that back in 2004 in Manchester, a couple of guys and their colleagues, Andrei Geim and Kostya Novoselov, published a paper in which they mentioned single-layer graphene. And from that came many, many things, not the least that they got the 2010 Nobel Prize in Physics. Now, they were working just next to chemistry, where I work in Manchester. And the same year, a colleague and I, Neil McKeown, he's now at Edinburgh University, we published a paper on a class of polymers that we call polymers of intrinsic microporosity, or PIMs. And so these two things arrived in Manchester in the same year. One thing we did actually is the year before we filed a patent application. And I like to think that, that we beat graphene to an application, I'll say a bit about this later, to an application that relied on the material for its function. Graphene quite early on, it was put into tennis rackets, and maybe it gives a little bit better performance, but let's face it, it's still a tennis racket without the graphene. So my argument is that in terms of something that wouldn't work without the material, we beat graphene. But I've also got involved in graphene research, and I'll say I can't escape it. And I have to say that Andrei and Kostya, well, they got the Nobel Prize. Neil and I, we haven't had quite such recognition or quite so much money poured into it. But they're both interesting areas, and I'm going to talk about each of these and also about how we can bring them together. But I'm going to talk first about our polymers, because you probably know, probably most people here have at least heard of graphene, is that right? And probably most of you haven't heard of PIMs, is that right? So I'll tell you a bit about PIMs, and then we'll come back to graphene later. And we call them polymers of intrinsic microporosity. Now, this is using the word microporosity in a very specific way, because like a lot of words, that gets reused in different ways in different bits of science and engineering. But in the context where we're thinking about how little molecules interact with a surface, where the surface may be an outside surface or actually an internal surface inside a material, the surface of a pore, a space within a material. In terms of that absorption, then the International Union of Pure and Applied Chemistry has a definition which separates out materials according to pore size, in terms of how big those pores, which is actually based on the different mechanisms of absorption that can occur. And the very smallest pores in this context, those which are not much bigger than molecules, less than 2 nanometers in dimension, they are what in this context is called micropores. And then when you get a bit bigger than that, things change. And when you get big, you have mesopores, a bit bigger than that, things change again, and you have macropores. But it's that micropore region that particularly interests us, because that's the region where something which, even though it interacts weakly, you've got a little molecule, if you put it in a pore, which is quite small, it feels the walls all around it. So the interactions between that little molecule and what's around it get magnified, simply because it's in a small space. And you get extra strong adsorption, an extra liking, if you like, just because the holes are small. And so that's a really interesting region to be working in terms of trying to work out how to selectively move things out of a mixture and through a medium somewhere else, which is a lot of what we're interested in. And when we talk about polymers of intrinsic microporosity, we've got something which behaves as though, and we're kind of on the fringes of what you would call a pore, what you would call something else. The phrase we use is free volume. But behaves as though it's got those little tiny pores, spaces that little molecules can get into, and where they interact very, very strongly, just because the spaces are so small. But we create this not through some fancy processing or engineering or how we do things, but right at the level as a chemist of how we actually design the molecular structure. And so our idea here is that what we have is we have a material within which we have interconnected spaces that little molecules can get into, but they are there, they arise because of something to do with the actual structure of the molecules that we're creating. And chemistry is an incredibly creative subject. Often we think of creativity as involved with the arts, but you can't be more creative than a chemist who takes the very raw materials of the universe and works out how to construct things that have never before existed. It's fun. Okay, and the basic concept is quite easy. Now, a polymer is a big molecule, and the simplest case, it's a big, long, wiggly molecule. Okay, it can be more complex than that, but basically, are we all happy with the concept of a molecule? And these are big, long, wiggly molecules. And typical polymers, you can think of it as like snakes. They're all big, long, wiggly molecules, and given a chance, they can wiggle around and do their best to fill space. Now, we can design polymers to have very, very actually rigid, extended structures if we want to. But then they tend to actually interact with each other very strongly and pack together, and you really can't do much with them. So the basic concept that underlies our polymers is that if we can make a molecular structure which is long and wiggly, but can't reorganize itself, can't wiggle around actually as much as a normal polymer, we have something which can't effectively pack down, which leaves a lot of extra space. It's like the difference between spaghetti and crispy noodles. You know, if I think of a plate of spaghetti, it can sort of, you know, there's bits of space, but crispy noodles can't pack down so effectively. We're creating polymeric crispy noodles. And then that space that little molecules can get into, and because they're little spaces, we have this extra strong attraction that we're talking about. So the first, the prototypical, we made a few, but the one which has been most studied, and the one we actually call PIM1, because it illustrates things, is this structure here. And I've got a model so we can hopefully see something about how it works. So what we've got is a backbone. Now, can you tell the backbone? It's all little rings joined together. What there isn't in this polymer is what we call single bonds. And that means, okay, it can wiggle like that, but if you try to rotate, you can't rotate it very far without breaking a bond. So we've taken out a lot of the flexibility that exists in a normal polymer chain. But we have made it wiggle around, or appear to wiggle around. We do that, and now we've just broken a bond here, by having what we call a spirocenter. So if you've done some chemistry, there's a carbon atom here which sits between two 5-membered rings. And what that does is it puts a bend in the chain. The next one puts another bend in the chain. It's all randomly oriented, so it wiggles around randomly, but it can't change, except when your model is a little ropey and it keeps breaking apart. It can't change its structure in the same way as a normal polymer can. So those are the basic ideas behind a polymer of intrinsic microporosity. First of all, it has a rigid ladder structure made up of fused rings. There are no single bonds about which rotation can occur. Sometimes, for the chemists amongst you, have we got some chemists amongst us? People have done some chemistry? yeah, right. Sometimes you can get away with a single bond if you've got very highly hindered rotation about that bond. So you have a chunky group by the bond. But in this case, we have no single bonds in the backbone at all. And so we've taken out a lot of the flexibility that a normal polymer chain has. But we have built in these wiggles, the things that make it like a crispy noodle rather than spaghetti. And in this case, it's a spirocenter, but there are other chemical things that we can do to have the same effect. So those are the two basic things you need for this type of polymer. And that's the basic concept that we're working on. but the thing about this is what we now have is a polymer. This is we talk about microporous materials. There are a lot of microporous materials, zeolites. Actually, the simplest thing is to take almost anything and sort of burn it under controlled conditions to get a carbon. But the trouble with those things is you can't easily shape them into different ways. Once you've got it, you can't do much with it. What makes these polymers different is that you can actually dissolve them up in certain solvents. Actually, I've got some here. This yellow stuff, the yellow color, if you look at, if any chemist who look at the structure might realize where the yellow color comes from. But this yellow stuff is that polymer, PIM1. And the thing about it is you can dissolve it up into certain solvents. That means you can process it from solution. You can make little films like, you can pass this around, why not? Little films out of it. And that film behaves like a microporous material. And so what makes these things interesting is that you can both process it and it has those properties that it will really absorb little molecules very effectively. And so you can recover it as a powder, but then you can coat it onto surfaces. You can make relatively thick films like the one that's going around. You can make it into fibers and all sorts of other things. And it's that processability that makes it particularly useful. In fact, this is what the origin of the first commercial application of this polymer. So here,
I have it.
so this is a mask that's made by the company 3M. 3M have a big business in personal protection. So if you're a factory worker, paint spraying, autos, or working in a composite factory, anywhere where there are a lot of organic vapors, volatile organic compounds, you might well wear one of these masks to protect you from those vapors. And what you have are little cartridges on the side, which actually contain an activated carbon. That's the old-fashioned sort of microporous material. It's basically something which has been, in the simplest case, burnt, but in a way to create lots of little bits of space. And that absorbs vapors very effectively. And so you will use that until that cartridge is used up, and then you need to replace the cartridge. Now, the question is, when do you replace that cartridge? Because you need to know, really, what the concentration of vapors you're working with, what vapors they are, how long you're breathing them and such like. And so probably if you're working for a good company, those cartridges would be replaced when they're hardly used. And if you're working for a bad company, you might be using them long after they've ceased to be effective. So the new thing on here, if we look, you see there's a little green window on the side of that cartridge. Yeah? So that little green window, the idea is that as that cartridge is used up, the little red bar will move across that window. So it's like a little sensor which gives you an idea of how much life is left in that cartridge. As long as, and the company is very, very careful on its advertising, of course, depending on what your environment is, ... lots of legals, right? But yes, so it's an end-of-life indicator. And our PIM is the key ingredient in that, because the way it works, have we got physicists here? We've got some physicists here. You know about interference colors, like the colors you get from oil on the surface of water. It's actually an interference effect that gives that green color. So the idea is you actually have a porous mirror adjacent to the carbon, so that will let vapors through if they get past the carbon. And then you have a very thin film of our polymer. That's where the processability is important. And then you have a non-porous half mirror. So light from the outside, some reflects off the top surface, some goes through the polymer, reflects over the bottom surface. That creates an interference color. It's set up so it looks green. If our polymer absorbs a vapor, and it absorbs vapors very similarly to an activated carbon, that changes the refractive index, also swells it slightly. Both things have the same effect. It changes the color that you see to red. So it responds to a broad range of vapors and gives you a good indication, because it responds at very low levels, of how effective that cartridge is. So that's the first commercial application of the polymer to actually be on the market. And that's why I say that I like to think we beat graphene, because that wouldn't work without the polymer. They actually, at 3M, they actually had the design of a sensor, and they were looking for a material, and out came our paper, and they thought, that's what we need. It's done a good many years in negotiations and license agreements and things, but hey. So, yes, so the cartridge contains an activated carbon to absorb vapors, and PIM1 is used in that sensor to indicate when the cartridge should be changed. So, a lot of our research is actually about gas separation, liquid separation membranes for separations. Because this is where there are a lot of big challenges. It's also a longer time scale because you're dealing with process engineers. And process engineers actually don't like new materials. It takes a long time, for good reason, to persuade them to take on a new material. So we're working towards that. But you may not realize that you've probably actually benefited from gas separation membranes. They are used in a number of areas. Actually, if you've ever flown in a commercial jet aeroplane, you may not realize it, but most of them actually these days have a membrane system on board which feeds an inert gas into the fuel tanks to reduce the risk of explosion. And the way they get that inert gas is they take some air, they actually bleed air off the engine, they put it through a membrane system which throws away enough oxygen that the gas that remains is inert. So that's the sort of area where membranes are already in use. Now, if you want to make a membrane for separations, there are two things you need, and then a load of other things actually to commercialize it. But first of all, of course, it's got to be selective. There's got to be a preference for one thing rather than another to pass through that membrane. A membrane is just a thin film. We have a mixture on one side, and what we hope is that one component of that mixture, either the component we want or the component we don't want, will travel through the membrane relatively easily, leaving behind everything else. So we need selectivity. But of course, in a real process, and this is where the chemists have to talk to the engineers to understand what goes on, it also needs to be productive. We need to get a lot of stuff through. And that can be expressed in terms of a flux, which is how much comes through per unit area per unit time, or in terms of a permeance, which takes account of the driving force, because you have to have a driving force, which can be a pressure difference or a chemical potential difference or something like that. And because that in turn depends on the thickness of the membrane, you can multiply by thickness to come up with a permeability. And each of those things are useful in different contexts. But essentially, there's always a balance to be found between selectivity and productivity. And the problem is that for the researcher, is that if you try to prove productivity, you usually find you've lost out on selectivity and vice versa. There's a kind of a trade-off between these two properties. And if we think about gas separation membranes, this is often shown in terms of a graph, a plot, where we actually plot selectivity against permeability on logarithmic scales. And in 1991, a guy named Lloyd Robeson collected together all of the data for all of the polymer membranes that had ever been studied up to that time. And he plotted all the data on a plot like this, and he drew a line through the best points. And that was, if you like, the upper bound of performance. That's the best that could be achieved. And what the idea is that at low permeability, you can get moderate. This is actually for air separation that we're showing you here, but you can do the same thing for different situations. Most polymers are actually not very permeable, but you can get them reasonably selective. And so matrimid is a polyimide actually that's commercially used, not very permeable, reasonably selective, not quite the best. The things that are the best performance often not used for other reasons. You can't scale them up, you're too expensive or whatever. And there are some polymers which are really, really permeable but not very selective. And actually not that much in between until we came along with PIMS, and we had something which broke that 1991 upper bound. And that was 2005, working with collaborators in Germany, that we published that data. So in 2008, Robeson went back to his plot and drew a new line. Now we had to try to beat the upper bound again. And my colleagues, friends across the world have been beavering away, come up with variations on the concept of PIMS. And so in 2015, for certain gas pairs, some fresh upper bounds were drawn. Carbon dioxide wasn't included then, but just last year, some colleagues came up with a new upper bound for carbon dioxide separations, again based on data for some new PIMS. Now, designing a new polymer, for a poor PhD student, that can be a PhD's worth of work, and actually for quite a few years, the reason why we still work with PIM1 quite a lot is it took us a long time to get a PIM that beat A poor student could spend months developing a new monomer, and then struggle to get it to make a polymer, and then struggle to turn it into a membrane, and then eventually got some data and it just wasn't quite as good as PIM1. And that's what a lot of research is like. Eventually we found ways of making new polymers. But then, of course, we realized that actually you can take the very first one, and if you just heat treat it in certain ways, you can get the same performance. And actually, this is work that was done here in Cambridge when Chili Song, when he was a PhD student, he's now a young lecturer at Imperial, but he did that work here in Cambridge, which demonstrated you could take PIM1 and an appropriate thermo-oxidative treatment gave performance just as good as any of the really difficult to synthesize new polymers that have been made. Still not necessarily easy to scale up, and we're still working on that sort of thing. So we think about carbon dioxide capture as one of the things that is of a particular interest. This is similar to the plots I've just shown you, but we've now got actually permeance rather than permeability on this axis, if you've spotted it. Because we talk about permeability when we're trying to compare materials, because we try to take out all of the other factors that matter. But if you're an engineer, you're actually interested in permeance. And of course, the way to increase permeance is to make the material thinner. But then you have other issues to think about. And also, you've got to get the right balance, because you might think what you want is a perfectly selective membrane. Well, actually, no, because if you want a process, you have to maintain a driving force. And if it's too selective and too permeable, something whistles through the membrane, and now you've lost your driving force, and now nothing happens. So depending on the process, you've got to get the balance right. So there's actually a region which is the optimum region to work in. And that's indicated here, and this is based on work done at a company in the States. And so to try to actually get in that region, it's an example of the sort of things we want to do. To get really high permeance, we want a very, very thin film, but a very, very thin film. So for example, it might be PIM1. We only want a few hundred nanometers ideally. But that then you can't use on an industrial scale. So we then have to support it on something to give it mechanical stability. In fact, in this case, this is some work we did in collaboration with some people in Moscow. We actually then have another layer, which is another polymer, which is much more permeable, and then another layer, which is even more permeable, but gives us the mechanical support. And the thing is that we can achieve performance right in the region that you want. The snag is we can't yet maintain that performance. So we're still working on that. And the reason is, the game we're playing is trying to squeeze space, put effective surface inside a material. And you may have heard the old saying, nature abhors a vacuum. Actually surface costs energy. And nature does everything it can to squeeze it out again. Our polymers are what we call glassy polymers. They're amorphous. They're kind of stuck but they're not quite stuck enough. They can still wiggle around if you give them a lot of time and enough sort of things to help them, then they will try to squeeze out of that space. It's a process called physical aging. And tackling that is the big thing, or one of the big things, to actually get these to function well over time. So that's current research which is ongoing. So I said a bit about the polymers of intrinsic microporosity. I'm going to come back to them. But I have to talk a little bit about graphene. And you probably know graphene, you've probably made graphene. If you ever drawn with a pencil, you've probably made graphene. Because graphene is, in the simplest case, a single layer of graphite. Because, of course, graphite has a stack structure where each layer is a carbon atoms arranged in a hexagonal pattern. And when we talk about graphene, in the simplest case, it's just one sheet of that. And you may know that the key thing that our Nobel Prize winners did, very simple idea. The difficult thing is proving it's what you've done. But a very simple idea, you take a bit of sticky tape and you take a bit of graphite and you keep pulling the graphite apart until you're left with just one layer. Actually, these days, a lot of the stuff that gets called graphene is now a family of materials. So, because, for some things you want a single layer, but a bilayer is still interesting. If you're making a composite, then most of the stuff that's actually put into composites is mostly multi-layer, because that's an awful lot cheaper to make and easier to make. But that still has a much bigger lateral dimension than thickness. So it's still a useful material. Perhaps not strictly graphene, but it's kind of comes under the family of graphene materials. If you've read things about graphene, you'll know all the superlatives that people say. It's very, very strong, at least for its cross-sectional area, thin, stretchable, high electrical conductivity, high thermal conductivity. The two things that particularly interest me in my field of work is its high surface area and its impermeability to pretty much everything. Actually, if you think about our polymers, so here we've got the graphene structure, which is lots of rings. Effectively, our polymer is just like taking a little ribbon of graphene and curling it up. That's why, A, it actually interacts very well with graphene, and B, it has an internal surface. The theoretical, if you have just a single sheet of graphene, then the theoretical surface area, given it's got two sides, is 2,630 square meters per gram. And in case you're wondering, that's equivalent to 10 tennis courts for every gram of graphene. And that surface is surface that little molecules stick to. That's where this adsorption becomes important. Actually, our polymer behaves as though it has, key phrase, behaves as though it has three tennis courts worth of surface area. So that yellow stuff, a gram of that is in terms of the amount of nitrogen it'll absorb under appropriate conditions, it's the same as having 3 tennis courts of flat surface. And it's that surface that's important for the interactions that we're interested in. And it's also in itself impermeable, but that still means it can potentially be used in membranes. So this is where I got involved in the graphene story when we started looking at membrane applications in Manchester. And there are a number of ways in which it can be used in membranes. The simplest idea, and the most impractical probably, is a single layer of graphene with little holes. And you can do that on a tiny, tiny scale in the lab, but very hard to think about how to actually turn that into an industrial scale product. But there are other ways. One is actually a laminate structure, which are lots of little plates that little things can get between. And the other is actually to use the graphene in combination with something else in a composite. And I'll say a little bit about both of those approaches. And there is an old YouTube video on graphene membranes that we put together quite a while ago when we were first getting involved in this sort of thing. Now we can work with graphene or we can work with derivatives of graphene, and a common thing for doing with graphene is to turn it into graphene oxide, which involves, usually you start with graphite, you oxidize it, you disperse it, you then have something which disperses in water, which actually is much more hydrophilic. That means it likes water much more than graphene does. And Rahul Nair, he was a PhD student with Andre Geim. He's now a professor in chemical engineering at Manchester. But he was the first person to demonstrate that you could make a laminate membrane of graphene oxide, and water went through it really, really readily. And yet in the dry state, it was impermeable, even to helium, the smallest gas that you can imagine. And so that was quite interesting, and we've got a patent going through the system which relates to the use of that sort of membrane for water purification purposes. And he's continuing to work in that sort of area and showing how, at least in the laboratory scale, you can create spaces tuned for different ions and such like. And that's picked up a lot of media attention. So graphene oxide laminate membranes, that's one approach that we're interested in. And another approach is to take either graphene or graphene oxide or a modified graphene oxide and incorporate into another polymer or another material. And this is one area where these two types of materials, the PIMs and the graphene, come together, because one thing we've been doing, of course, is putting graphene and modified graphenes into PIMs and seeing what happens, because actually they have a particular liking for each other, and we can use the graphene surface to control what's going on in a membrane. In fact, we can even, a few years ago, I thought you'd never be able to visualize a single sheet of graphene in an organic polymer. But we've got some really good electron microscopists at Manchester who found ways of doing that. So I'm just going to mention one area of interest, industrial biotechnology, which is where you take biomass, that's plant matter or something like that, you put it through some sort of process, and usually you end up with a dilute aqueous mixture that you've then got to separate out. So this is another example where you need separations, because very often that separation stage is the bulk of the cost of a process if you want to develop it. And one process which again has its origins in Manchester, Chaim Weizmann was in Manchester University before the First World War and developed a fermentation process which has become known as the ABE, the acetone butanol ethanol process, because it produces a mixture of 3 different compounds. If you know Chaim Weizmann, he went on to a very different career. From chemistry, he became the first president of Israel. But during the First World War, that process was actually really important because we used to get our acetone from Germany. For some reason, supplies were a bit of a problem. And so they used ABE fermentation to produce acetone, which was needed for cordite. And actually, they were using potatoes and maize to feed the fermentation process. So there's a conflict there. And this is often a conflict you have in industrial biotechnology between food uses and industrial uses. So they looked at alternatives. They thought of conkers, horse chestnuts. In fact, in 1917, they had all the boys. It appears to be mostly boys. I'm sure some girls were involved as well. But going around, mobilized to pick up conkers, and they accumulated vast quantities of conkers at railway stations. I don't think the process worked very well. I don't think they had the I think most of them rotted at the railway stations. They didn't have the transport to move them. And the next year, the war was nearly over, so I don't think they organized the conker collection again. But they had a go at it. But then petroleum became, as is often the case, a much cheaper way to get these things. But now, of course, we're looking at alternatives to oil-based things, and variations of the ABE process are back in vogue. So membrane processes are being used as an alternative to distillation. I'm going to move fairly quickly because I want to give you plenty of time for discussion. There's a membrane process we're interested in, which is pervaporation, which is a combination of permeation and evaporation. The important thing is our PIM polymers, they're amongst the few things which will pull an alcohol out of water, potentially. And the key thing is we can start adding graphene derivatives and actually improve that separation. This is one area where we can put 2 materials together and improve the performance. Another thing I mentioned briefly, we can actually make our polymers now as 2D materials. This is something that's just been published, where we create a network PIM, which if it's a tightly cross-linked enough network, much to our surprise, it came out as 2D nanosheets. But what I want to say a little bit is why I do research anyway. And perhaps the first thing is not to do with money. We need money to do research, but I took a significant cut in salary when I left BP and became an academic. The first thing we do, it's fun. It's fun. I love having an enormous chemistry set to play with. Even if these days it's the students and postdocs who have all the fun, and my job seems to be trying to keep them going by bringing in the funding and all the rest of it, but hey. And of course we do it because science is actually a very, very good way of getting answers to certain sorts of questions. And there are a lot of interesting questions out there that science gives, science is the way to get those answers. But of course there are some questions that science can't answer. Questions of morality. What's right, what's wrong? Actually, scientists need certain morals. Science doesn't work without honesty. But morality is something a scientist brings to the subject. It doesn't arise from it. And of course, it can't answer by itself the question, is there a God? But science is useful. And you will have seen, actually my research, we are trying to answer fundamental questions actually about how molecules interact with each other. But because I'm in materials research, we also always have our eye on a potential application. And so I don't see a distinction between pure and applied research. It's a spectrum. And science is useful, and I hope I've shown some of the ways which it's potentially useful for solving some of the challenges that face us as a society. And the other thing is actually, I believe that science helps us learn something about God. And I'm not the first person to say that. Probably many of you know that Johannes Kepler, the guy who worked out that planets go in elliptical orbits, he wrote laws of nature, laws effective of nature are within the grasp of the human mind. God wanted us to recognize them by creating us after his own image so that we could share in his own thoughts. That's often been paraphrased as thinking God's thoughts after him, though I don't think he ever actually wrote that himself. And of course the Bible, if you believe in the Bible, has this verse in Romans 1:20, for since the creation of the world, God's invisible qualities, his eternal power and divine nature have been clearly seen, being understood from what has been made. In other words, we can learn something, not everything, not all we need to know, but something about God from studying the world around us. And science is a beautiful way of doing just that. One guy who spent all his working life around Manchester was James Prescott Joule. His father had a brewery in Salford. And you may know his name now is attached to the SI unit of energy. But of course what he did is he did a lot of detailed experiments on the relationship between heat and work. He laid the foundations of what became known as the law of conservation of energy, which led into the first law of thermodynamics. And if you ask, what got him to pursue that idea? Well, in one of his papers, actually, he says what motivated him in the way he was thinking. It says believing, we probably wouldn't write that in a scientific paper nowadays, but he did, believing that the power to destroy belongs to the Creator alone. In other words, his concept of God actually fed into how he developed his science. And I don't think it's any accident that science actually arose in a context in which, by and large, actually people did believe in God. Because science actually relies on the concept that there's a pattern, that there's regularity in nature. You know, that if my student does an experiment in my lab today, somebody else, the other side of the world, should be able to reproduce that experiment. That assumes there's some sort of absoluteness, some sort of order in the universe. Which makes perfect sense if one believes in a God who is consistent in character and behavior, that one naturally leads into the other. Which is another reason why I find it very strange when people suggest there's some sort of conflict between science and faith. And I've run out of time, but if we've got a bit of time, it's open for discussion.